In the previous lecture we saw how to apply residue theorem and evaluate certain improper integrals. Okay. In this lecture we see there is some local theoretical property of analytic function, the zeros of an analytic function. What do you mean by zero of a function? I mean the point at which the function is 0. Okay. So Z0, so suppose Z0 is a point, the complex number, and if Z0 is 0, then we want to call Z0 as 0. Okay. So Z0 is called 0 of f if Z0 is 0. Now simple type of functions that we know, alright, where we can easily compute the zeros, probably at least polynomials of lower degrees, that is suppose if I just write z, if z is z, then z equal to 0 is a 0. Suppose if I write z minus 1, z equal to 1, so I write z minus 1 and to z minus I. 1 and I are zeros. Okay. So in general, if you have a polynomial Pz, that is suppose a0 plus a1z to a n z power n, then what can you say about the zeros of P? What can you say about the zeros of the polynomial function? So let's first talk about the polynomial function and then go to general analytic functions. Okay. In case of polynomials we call roots. Okay. So what can you say about the roots of a polynomial? How many roots are there to this polynomial? The degree is n. Okay. Then it has n zeros, right? It has n zeros counted according to multiplicity, that is some root may repeat, some root may occur 4 times or whatever it is. So Pz has n roots, that is fundamental theorem of algebra actually. That is what it says. So it has always a complex root, and then in turn it implies that whatever is the degree, it has exactly n roots. Some roots may be repeating. Okay. So Pz has n roots. Okay. So in the plane, these are say n points at which this polynomial will become 0. Okay. So I want you to just observe how the 0 set would look like. Okay. So in case of polynomial it will look like this. I mean there may not be, some point can be here or here, but somewhere in the complex plane this n points, okay, we can show geometrically where and at all other points this polynomial is analytic function. I mean it is analytic everywhere, but it is non-zero at all other points. Okay. So important thing is that suppose this is a 0 of the polynomial and this is another 0, then I can find always a neighborhood because there are finitely many points. Alright, maybe I can find the distance between these 2 points, or from this point the shortest distance to any other point, and find a neighborhood such that now in this neighborhood there is no other 0 of the polynomial. So I can always find neighborhoods of these points where these zeros are separated from each other in the sense that in that neighborhood that is only 0 of the polynomial. I can do that, at least in case of polynomial. Is this clear to you? Because there are only finitely many, okay, and finitely many points, you take any point and find the distance with that point with all other points and take the minimum, and you can take always a neighborhood which has a smaller radius than that. then you can always isolate that point from the rest of the zeros. So all the zeros can be isolated from each other, that is the set is an isolated set. So in the other course on topology, if you have seen already what a discrete set or an isolated set means, that means the point of that set, you can find a neighborhood such that there is no point of the set lying in that neighborhood. That is the only point lying in that neighborhood. Is this clear? So this fundamental theorem of algebra tells us that polynomial of degree n has n roots. Okay? And then therefore further we can say that the zeros are therefore isolated. If you take any polynomial, the zeros form an isolated set. Okay. So actually before going to any general analytic function, we would like to think about polynomial. Alright. So whatever perhaps we can think about a polynomial, we would like to do that in case of an analytic function. So by virtue of fundamental theorem of algebra, there are exactly n roots to polynomial of degree n, and therefore naturally being finite set, it is a discrete set, and you can always isolate one zero from the rest of the zeros. Okay. Now we wonder whether the same thing happens for any analytic function. Okay. So if I replace this polynomial by some other analytic function for that matter, so suppose if I take say sin z, what happens? Okay. So that is what we want to think, whether the zero set has a similar property that we can isolate one zero from the rest of the zeros. That is the question. So something that is true for polynomial, we would like to check whether that goes through for an analytic function. Okay. Other important property for polynomial as far as a zero is concerned is that suppose z0 is a zero. So suppose a polynomial has root say z equal to 1. Okay. So suppose 1 is a root of pz. Okay. Then what can you say about the factor pz? You can take out the factor z minus 1, right? Once this is a root, you can have z minus 1 as a factor, right? So you can always write in that case pz equal to z minus 1 times say qz. Okay. And then you may again check whether 1 is factor of this, and then as many times the root 1 occurs. Okay. So suppose it is of multiplicity m, that means it occurs m times. Okay. Then you can write that as z minus 1 times m into some other say q1z, where now there is the 1 is not a root of this. Is this clear? So this we can do for a polynomial. So 1 is a 0 of this polynomial, then z minus 1 factor could be taken out. Now can we do this for a general analytic function? That is second question that we would like to pose. So there are two things that I have asked you, that we are thinking about, whether the zero set is discrete just like polynomial. Okay, if you take any analytic function, will the zero set be again discrete? And the other question is, can we factorize? So this factorization theorem, will it go through for any analytic function? Okay. So alright, so let us go to, so what are zeros of sin z? Now let us go from polynomial to any other analytic function. So what will happen to sin z? What are zeros of this? What are zeros of sin z? 0, 0 is a 0 and pi. Can you tell all the zeros? N pi, that's right, very good. So zeros of, or the zero set we can say of sin z are points n pi, okay, where n is integer, alright. Now can you say that this is also a discrete set? Can you isolate one zero from the other? Can you find a neighborhood such that in that neighborhood that is the only point where it will be the 0. So these points are 0, pi, 2 pi, minus pi, minus 2 pi and so on. Okay. Now I can isolate this. I can find neighborhood. Okay. In the complex plane, of course, these are we looked upon as roots of sine z. Okay. But still I can find neighborhoods, right, where the zeros can be isolated. Okay. So now we can guess that, just like a polynomial, it might happen that the zero set of any analytic function is a discrete set like this, where any one zero is given, then we can find a neighborhood around that, such that that neighborhood will not contain the other zero. Is this clear? This is our objective, that is, we want to show that the zero set of a analytic function is discrete set. And discrete set means we can isolate one zero from the other, or we can find a neighborhood such that there is no other point of that set. Okay. Now some other examples are like, what are zeros of e to the power z minus 1? What are zeros of e to the power z? What is zero set of this? So let me call as this zero set of this, okay, or maybe I will use some other later. Okay, zero set of this is what? There is no zero, it is empty. Okay, so zero set of this is phi. Is this clear? What about e to the power z minus 1? E to the power z minus 1, 0, and that's it. Okay, it is singleton 0. It is singleton 0, right? Now let us see e to the power, okay, let us consider z sin z, the function z sin z. What are zeros? 0, pi, 2 pi, 3 pi, like that. So 0 and, so let me call z1 equal to 0 and z2 equal to say pi. Then both are zeros. But what is difference? Some kind of nature of the zero. Can you say that one is different from the other, or the multiplicity, number of times it occurs? I am just asking intuitively whether 0 is also 0 of this function. Okay, fz is this, and pi is also 0 of this. So f of 0 is 0, f of pi is also 0. But then there is some difference in these two. Can you tell what? 0 is repeated root. Do you think that? I mean, do you really think like that? That 0 is a repeated root of this? Intuitively it is also in sin z, also z equal to z function also it is 0, and sin z is also 0. But then we want to make this precise, alright. So what I do is I find f dash z. Now what is f dash z? It is sin z plus z cos z. Now if I put z equal to 0, it is 0. So f dash of z1 is 0. Whereas what about f dash of pi? It is sin pi 0, pi cos pi. Cos pi is minus 1. So it is minus pi. So that is not 0. So after finding first derivative, the difference between these two zeros is more clear. That is, at this point f dash is also again 0. But at this pi f dash is not 0. And now if you say consider f double dash, okay, f double dash will be cos, that is 2 cos, and minus z sin z. Okay. So f double dash z is 2 cos z, right? This is cos z, this is cos z, and plus minus z sin z. So f double dash 0 is not equal to 0, right? It is 2 in fact. F double dash 0 is not 0. So, but had I taken z square, you imagine z square here, z square sin z, then f double dash 0 also would have been 0. Or had I considered z sin square z, what would have happened? Then even pi will occur again. Okay. Alright. So, see, in case of polynomial, it is easy to define the multiplicity of the root because finitely many roots and you can actually count how many times a certain root occurs. Okay. So, some root occurs 2 times, but now if you take an analytic function and if we want to define multiplicity of the 0 or the root, then how do we, then we use this concept of derivative. Okay. So, now I am going to define 0 of order m. 0 of order m. So, z naught is called a 0 of fz of order m if f z naught equal to f dash z naught f m minus 1 derivative at z naught all are 0 up to that, but mth derivative at z naught is not equal to 0. Like here, the first derivative at z1 is also 0, f z1 is also 0, okay, f dash z1 is also 0, but f double dash z1 is not equal to 0. So it is 0 of order 2, m minus 1, okay. So m is 2 in that example, okay. So 0, so say z equal to 0, so let me call z naught is a 0 of z sin z of order 2. Now we come to know how to decide the order of the 0, alright. Clear? What is 0 of order m? So suppose you may take, say, z raised to 100 sin z. Okay. All right, z raised to 100 sin z. Then this is 0 of order 101. Okay, because you can check that 100 k from 0 to 100 it will be 0. Okay, when you have enough time you can check that, but then don't get into that. All right. Now the important theorem which I call as factor theorem for analytic functions. See, we have factor theorem for polynomials, alright. As a corollary of the division algorithm, we have a factor theorem. That means what? So let us write first of all for polynomials what is factor theorem. Okay. So if, alright, so factor theorem. Factor theorem says that, now I am writing for polynomials, right? So you may just see this, you need not write this. So if Pz is a polynomial, and Z naught is a root of Pz of multiplicity m, of multiplicity m. Then Pz can be written as, okay. So I am assuming that it is monic and all that, but that is all right. Z minus Z naught raised to m into Qz. So you don't have to have also monic. Q can coefficient leading term could be anything. So this is Z minus Z naught to the power m into Q. Okay. This is factor theorem. This you must have done. This is for polynomial. This is just by division algorithm. That is, if Z naught is a root, then you divide Pz by Z minus Z naught, and then you observe that the remainder is 0. Again it is a root, you again divide the quotient, okay, and then you keep dividing till it is not a root, and then you get, so Qz naught is not equal to 0. Now this word multiplicity I have replaced in case of analytic, in case of any function for that matter, okay, as by order of the 0. But now I take analytic function. As a generalization of a polynomial, I take analytic function, and then a similar factorization theorem will occur. That just like you can factorize a polynomial, you are also able to factorize an analytic function. Okay. So this one can call as factorization theorem for analytic functions. Okay. Factorization of an analytic function. How do you factorize that? That means so suppose fz be analytic now, okay. So a function fz is analytic at z naught and has a 0 of order m at z naught and has a 0 of order m at z naught if and only if and only if there exists a function g analytic at z naught and what do you expect? See, polynomial is this into some polynomial. So I expect that fz is z minus z naught to the power m into gz. Okay. So and fz is z minus z naught to the power m into gz. Okay, where gz naught is not equal to 0 because you order m, alright. Gz naught is not equal to 0. So now you see these two theorems, they are exactly of the same type, okay, where here if you start with polynomial, you get a polynomial. If you start with an analytic function, okay, you get an analytic function. So analytic function is z minus z naught to the power m into some other function which is also analytic at z naught. Okay. So and converse is also true, that is, suppose if the function is of this type, then f is analytic and f has 0 of order m. See, this condition is for function to have a 0 of order m. Okay. If you remember, now you compare it with our theorem for pole of order m. It was gz upon z minus z naught to the power m. Okay, is this clear? Now this is gz into z minus z naught to the power m, because this has z naught as 0 of order m. So this is necessary and sufficient condition for an analytic function to have 0 of order m. So f is analytic at z naught, that is important, and it has 0 of order m, then this will happen and converse is true. That means if there is a function g analytic at z naught, gz naught is not 0 and f is of this type, then what will happen? F has 0 of order m at z naught. Okay. So let us try to prove this theorem. Okay. So let us consider the proof. The proof of this. Okay. So let us. I can take the board close to you. Okay. So proof. And the statement is has gone, but you know the statement now. Okay. So there are two parts. All right. That is, first we assume that f has 0 of order m. So suppose, part 1 is, suppose f is analytic at z naught and f has 0 of order m at 0 of order m at z naught, 0 of order m at z naught. Okay. Now, what do you know about analytic function? I mean, this analytic function, somehow you want powers of z minus z naught, then you will have to think about the Taylor series expansion. See, somewhere this z minus z naught to the power m should come out, but f is, nothing is known about f. But then you can use the theorem that f has Taylor series expansion. Then f has these representations in the powers of z minus z naught. So it is therefore a good hint that what is to be used. We have to use Taylor series expansion. Okay, because we want some powers of z minus z naught. So f is analytic at z naught means there is a neighborhood of z naught in which f has Taylor series expansion. That means you have this neighborhood. So for any z, you can write fz in terms of powers of z minus z naught. So there exists R positive such that for z in the neighborhood of z naught, what happens? Fz can be written as sigma an z minus z naught to the power n. But that an is also determined from this, that is f nth derivative at z naught upon factorial n z minus z naught to the power n, n from 0 to infinity. This is what you have. Okay. Now apply the definition of f at 0 of order m. Okay. What is definition of f at 0 of order m at z naught? First, I mean f z naught is 0, f dash z naught is 0, f double dash up to f m minus 1. But then you see this term. So what is first term n equal to 0? That is f z naught. That has to be 0. What is second term? F dash 0. That also has to be 0. So up to n equal to m minus 1, all terms will be 0 because it is given that f at 0 of order m. Okay. So this series will really start with what? Z minus z naught to the power m, and here also mth derivative. So thus, but as f has 0 at z naught of order m, fz can be written as sigma n from m to infinity, right? F nth derivative at z naught upon factorial n z minus z naught to the power n. Starts with m. So first term is, and now you also know that mth derivative is not 0. Mth derivative is not 0. Okay? Because why? 0 of order m. So if you take this z minus z naught raised to m, that is first term, which is outside now. Now you can take that out by the product of polynomial and a power series. Summation. Now I can write what? N from. So this I have taken out. So this is equal to what? This is plus n, m plus nth derivative. Okay, and I can write m equal to 0 to infinity, m plus nth derivative at z naught divided by m plus n factorial and z minus z naught to the power m plus n. Okay. Because if you put n equal to 0, then you get mth derivative. Here it will be n. Here it will be n. So constant term is, after taking z minus z naught outside, the constant term is what? N equal to 0, okay, which is mth derivative at z naught. This is nothing but, see, this is nothing but what? Mth derivative at z naught upon factorial m into z minus z naught to the power m and so on. So when you take this term outside, this becomes the constant term inside. That is n equal to 0. Okay. N equal to 0. Is this clear? Now, what we can really do is that call this function as gz, right? Because we want fz to be z minus z naught to the power m into gz. Where what is property of g? Now gz naught is what? Mth derivative at z naught. So gz naught is this series. I call it gz. So gz naught, which is nothing but what? Mth derivative of z naught upon factorial m, correct? Because you put z naught, then the rest of the term will be 0, because if you take n equal to 1, then z minus z naught will come and that will be 0 at z naught. So only constant term will survive when you put z equal to z naught. But constant term is mth derivative at z naught upon factorial m. But we know that z naught is 0 of order m. So this is non-zero. Okay, so this is not 0. So gz naught is not equal to 0. That is how the theorem is stated. See, gz naught is not equal to 0. That is what we wanted. Alright. So we have expressed fz at z minus z naught to the power m into gz, where gz naught is not equal to 0. Clear? So one part we have done. Now we want to show that if f is really of this form, then what happens? Then we want to show that f has 0 of order m. So now let's start with that. So suppose, now part 2 is that suppose fz has this representation in some neighborhood of z naught, okay, z minus z naught to the power m into gz, where gz is analytic at z naught. Okay, where what is given? Where gz is analytic at Z naught, and G Z naught is not equal to 0, that is given. G Z naught is not equal to 0. But G is analytic at Z naught means what? G has a Taylor series expansion. G has Taylor series expansion in the neighborhood of Z naught. So there is some neighborhood of Z naught where you can expand G. So at G is analytic at Z naught, G has Taylor series expansion. In some neighborhood of Z naught, okay, and that Taylor series expansion will be Gz equal to what? Nth derivative at Z naught. So Gz is equal to summation nth derivative at Z naught by factorial n, Z minus Z naught to the power n, n from 0 to infinity. Now if you put it here, this G, then what is Fz? Therefore Fz is Z minus Z naught to the power m summation n from 0 to infinity, nth derivative at Z naught, Z minus Z naught to the power n upon factorial n. Now I can multiply inside, okay. So this is equal to summation nth derivative of Z naught upon n factorial n from 0 to infinity into Z minus Z naught to the power m plus n. Remember, these are constants and these are powers of Z minus Z naught. This all happens in some neighborhood of, so in n r Z naught, right? So for Z belonging to this, okay, so let me write for Z in this, all this happens. For Z belonging to this happening. But then you see that Fz has a power series expansion, that is it has a representation in powers of Z minus Z naught in some neighborhood of Z naught. But that means what? That means F is analytic, because that also we have seen that if you have a series expansion, then you can further differentiate that and you get a series expansion. That means series expansion, if certain function have in powers of Z minus Z naught, then F is analytic at Z naught. We have already seen that. So this, and then by uniqueness of the Taylor series, remember that also is important point, that function F has a power series expansion in the neighborhood of Z naught, okay, then that has to be Taylor series expansion of F in the neighborhood of Z naught. So these coefficients must be the coefficients as they would have appeared in the Taylor series expansion of F, but they are what? Derivatives of F, that is f z naught, f dash z naught, f double dash, like that. Now what is constant term in this? It is 0. Do you see that? Because if you put n equal to 0, so this series starts, this particular series of F, now this z minus z naught raised to m has gone inside. So this series of F starts with what? Z minus z naught to the power m. So as a power series expansion in Z minus Z naught, first terms, that is fz naught, f dash z naught, f double dash z naught, are not appearing. They are 0. Since this is Taylor series expansion, this actually is what? Fz0 plus f dash z0 into z minus z0. But fz0 is not appearing. So that must be what then? 0. F dash z0 into z minus z0 is not appearing. So that has to, f dash z0 has to be 0. The coefficients have to be 0. So by uniqueness of the Taylor series expansion actually, so by uniqueness of the Taylor expansion, we get what? Fz0 is 0, f dash z0 is 0, and so on up to m minus 1 derivative of f at z0 is 0. But what is mth derivative? That is coefficient of z minus z0 raised to m. But that means n equal to 0. That means what? gz0. And mth derivative at z0 is gz0. But it is given to us that gz0 is not equal to 0. So mth derivative is not equal to 0. See again. The coefficient of z minus z0 to the power m is nothing but putting n equal to 0. So that is gz0. But gz0 is already non-zero. Okay. That means coefficient of z minus z0 to the power m in the Taylor series expansion of f is mth derivative at z0 upon factorial m. So this must be equal to this, but this is already non-zero. Now what do you get? That f is analytic. Okay. So first of all, this gives f is analytic at z0, and then f has 0 at z0 of order m. Okay. F has 0 at z0 of order m. Now, at the beginning of the lecture, we posed a question that whether the 0 set is discrete. That means whether I can isolate one 0 from the other. That means can I find a neighborhood which will not contain any other 0. Okay. Now once we have this factorization theorem, okay, we are able to prove that the 0 set is really a discrete set or an isolated set. Any terminology is used. Okay. Discrete set or isolated set. So let me define a discrete set. So a set S is discrete if for any z0 in S there exists delta such that n delta z0 intersection S is just z0. I mean, it does not contain any other point. That means your set S may have some more members, but then every point, any point you take, now this delta will depend on z0, okay, because your set is suppose like this, one point is here, then you want what? Every point you want to find neighborhood such that it will not contain any other point of the set. So here you may be able to take a larger neighborhood, here you may have to choose neighborhood which is smaller. But the point is every point there is delta. This delta may depend on this point, such that if you take the delta neighborhood of Z0 and intersect with the set, it will not contain anything else, because this will contain Z0 and intersection will contain only this point of S. Okay. So now other points of S are outside this neighborhood. So is the definition of discrete set clear? And then we want to now prove that the zero set of any analytic function is discrete. If you take any analytic function, the zero set is discrete. We have evidence of polynomial, okay, and also sine function we have seen as an example, but the strong evidence comes from polynomial, which is a finite set. But now if you take some non-polynomial analytic function, it can have infinitely many zeros, but still it will form a discrete set. Is this clear? Okay. See, as against that, if you consider a function of the type, say suppose if you consider sine 1 over z, okay, if you think of function sine 1 over z, let us consider this. What are zeros of this? What are zeros of this function? Now zeros are 1 upon n pi, right? That means if you put z equal to 1 upon n pi, then this becomes sin n pi. So zeros are, so zero set is 1 upon n pi, n in z. Okay. Now if you consider 0, okay, of course the function is not analytic at 0 here, function is not analytic at 0, okay, it is analytic everywhere except 0. Now this sequence converges to 0, remember 1 upon n pi will converge to 0. So if you consider a neighborhood of 0, alright, okay, then all but finitely many terms of this sequence will belong to that. Alright. So you will not be able to isolate if you consider a neighborhood of, alright, if you allow 0, of course the function is not analytic, but then if you just think of whether it will also hold for some other functions which are not analytic, then you may define this function to be something at z equal to 0. So this is when z is not 0, and I may define that equal to 0 if z is equal to 0. That won't be analytic. But then the 0 set is not discrete then. It has a limit point. It has a limit point 0. That means every neighborhood will contain all but finitely many terms. They will cluster. 1 upon n pi will cluster around 0. So you won't be able to isolate. I mean, if you take delta neighborhood of some 0, then you can find other zeros in that neighborhood. In fact, alright, many zeros you will be able to find out in that neighborhood. So here we are taking analytic functions, and in analytic function this will not happen. For analytic function, if you find out the 0 set, it will be always a discrete set, right? It means all zeros can be written. So if f is analytic, the 0 set is discrete. So let me call this as a theorem. If f is analytic at z0, if f is analytic at z0, if z0 is 0, that means z0 is the 0 of f, okay, and f not identically 0 in any neighborhood of z0, and f not identically 0. F is analytic at z0, f z0 is 0, and f is not identically 0 in any neighborhood of z0. any neighborhood of Z naught. Okay. See, if you consider a zero function, fz equal to 0, then that is constant function and that is analytic. And then it is everywhere in a certain domain if you consider, okay, constant zero function, okay, on a certain set. Then now this is also 0 of the function, this is also, now you cannot isolate. Okay. So I have to take a function which is not identically 0 on any neighborhood. So if you take any neighborhood of z naught, okay, so suppose if you consider z naught, okay, fz naught is 0. But in any neighborhood, like it will not be identically 0. Identically means at every point in that neighborhood f is 0, that is not happening. Okay. Later on we will see if for an analytic function defined on a domain, on an entire interval, this neighborhood, if it becomes 0, actually it becomes 0 everywhere in that domain. So if this is defined on this domain and it is, suppose it is 0 throughout a certain neighborhood, then it will completely become 0 on throughout D. Okay. But it is assumed that it is not 0 in any neighborhood of Z naught. Then there exists epsilon positive. Then there exists epsilon bigger than 0 such that fz is not equal to 0, fz is not equal to 0 throughout the set 0 less than mod z minus z naught less than epsilon. That means this is a deleted neighborhood of z naught. So see this picture now. That means you have this z naught, okay, and fz naught is 0. And this condition is given that in no neighborhood of z naught, however small you take, throughout the neighborhood f is not becoming 0. That is given to you. Then one can always find an epsilon neighborhood such that except for this point, fz is not equal to 0. That means some other 0 of f that will not come here. Fz is not equal to 0 means any other 0 will not come. Deleted means except z naught will be there. At z naught f is 0, but then it is not 0 at any other point. That means the other zeros are outside this neighborhood. So such epsilon will exist always. That is what we want to show. The proof of this is very simple actually. Alright. So proof is almost just a one line. Okay. Once you use this factorization theorem proved before this. So what was that theorem? Under these conditions, that if f is analytic at z naught and fz naught is 0, okay. Now this 0 may be of order m, suppose, okay. So suppose, see, it cannot happen that all the derivatives of f are 0, then f will be identically 0 in some neighborhood, because the Taylor series expansion will become 0, okay. So suppose f has 0 of order m at z naught. Then what will happen by earlier theorem? Then fz can be factorized as z minus z naught to the power m into g of z, where g is what? G is analytic at z naught, and most importantly what? Gz is not equal to 0. So g is analytic at z naught and gz naught is not equal to 0. Now analytic function is continuous. So if it is analytic at z naught, then it is differentiable at z naught and therefore it is continuous at z naught. Now if a continuous function is non-zero at a point, then do you know the property that there is a neighborhood of that point throughout which it is non-zero? See, by continuity, function is not 0 at certain point. Then it cannot happen that So you will always get a neighborhood throughout which it is not 0, because the absolute value will be strictly positive, and then you can choose delta such that in the delta neighborhood of Z0 again the absolute value will be strictly positive or things like that. Okay. So this is property of the continuous function actually. So by continuity of G, of G at Z0, there exists epsilon positive such that G Z0 is not equal to 0, Gz is not equal to 0 for all Z in epsilon neighborhood of Z0. If a function is continuous and non-zero at a point, then it is non-zero in throughout some neighborhood of that point. Okay. So you get this. Now this function is not 0 throughout epsilon neighborhood, and this is 0 only at Z0. So this will be non-zero except for Z0. Is this clear? That is what we wanted. So in the deleted neighborhood of Z0, Fz is not 0. Therefore Fz is not equal to 0 for all Z in 0 less than mod Z minus Z0 less than epsilon. Okay, this is the theorem I wanted to prove. In the notes that are given to you of this lecture, they are there. You may, I have sent a copy to the madam. Describe some more properties and corollaries of this, the principle of analytic continuation, or if a function. So let us see a simple application. So suppose if there is a function defined on a domain like this, and there is a line segment in this domain, okay, and then f is analytic throughout this domain D, and it is 0 throughout this line segment, suppose, okay, at every point of this line segment f is 0, suppose. So fz is 0 on L. Okay. Then what happens that if you take point Z0 on this line segment, okay, then even if I take any neighborhood, I can find other 0, because throughout L it is, so the condition of this is violated. Okay, that means if 0 is there, then it has to be isolated, because f is analytic. Okay, I have taken analytic map. Now the only reason it must be happening is that throughout certain neighborhood of Z0 f must be vanishing, okay, because under that condition we proved that the zeros are discrete. So now you must get a neighborhood throughout which f is 0. So throughout this function is 0. But then if you expand in the Taylor series of this, alright, you will get that all the derivatives are 0, because the function is identically 0, but it has Taylor series expansion in every neighborhood where it is analytic, alright. Now this is analytic in this neighborhood, so it has, so the function will be identically 0. Now there is some argument goes regarding connectedness of this space, which I have done there, but now there is no time, which proves that then it is actually completely 0 throughout D. Once it is 0 on a certain neighborhood, then it is completely 0. So if analytic function is 0 on a line segment or an open set throughout, then it must be a 0 function. There is no other choice. So if you take a non-zero analytic function, that non-zero means it is not 0 in the neighborhood of, every neighborhood of it is 0. There is some neighborhood throughout which it is 0 is not happening. Okay. So in any neighborhood it is vanishing, is not suppose the case, then the 0 set must be discrete, is isolated points. Okay. So that must be the case. Simple application is that suppose you want to prove that sin square z plus cos square z is 1. Okay. We have already done this by some other method, but now you can apply this theorem that you may consider the function fz equal to sine square z plus cos square z minus 1. Now we know the identity for real x, okay. So for all real numbers x, okay, which are now looked upon as complex numbers, you already have sine square x plus cos square x equal to 1. That suppose you have independently proved for real variable x, and we know that the restriction of the sine and cos functions to real is real sine and real cos. But this identity holds means what? F is identically 0 throughout line, real line. For x real, this function will be 0. So f is identically 0 on a line. That means f is identically 0 throughout the complex plane. That means this identity will hold for all z. Like that. Like that also you can prove possibly. So all the trigonometric identities immediately become true for complex variables. Because they are true for real variables, you take sine 2z is sine z, 2 sine z cos z. So consider the function sine 2z minus 2 sine z cos z. It is 0 already for x real. So it is 0 for the z complex throughout. So all the trigonometric identities will hold. There are some more interesting corollaries of this, and then you will get this. Okay. So thanks for your patient listening, and this was last lecture. I wish you all the best for your future career in mathematics. If you have any doubts, you can always contact at any time. But the formal course I declare that it is formally over. Okay. Thank you.